Magic, right? But it's actually just pure, elegant physics. Welcome to this explainer. Today, we're pulling back the curtain on this exact illusion to reveal the fascinating science behind how light bends, bounces, and totally shapes the world we see. We're diving straight into the principles of reflection and spherical mirrors. Basically, we're going to explore how taking a perfectly flat reflecting surface and just shaping it into a sphere gives us this incredible power to completely manipulate light itself. Okay, let's dive into this. Here is our roadmap for today. First, the rules of reflection. Then, we'll meet the spherical mirrors. Third, the illusions of image formation. Fourth, decoding ray diagrams. And finally, real-world mirror magic. Part 1, the rules of reflection, or the fundamental laws of light. Because, every magic trick has to start with some ground rules. Before we get into the complex curves and all those mind-bending illusions, let's quickly ground ourselves. Reflection is simply the bouncing back of light when it strikes a surface. It is the exact mechanism that lets us see literally any object around us that doesn't produce its own light. Now, what's really interesting about this slide is that these aren't just polite suggestions, right? They are the two unbreakable laws of reflection. Law number 1, the angle of incidence is always precisely equal to the angle of reflection. So, if a light ray hits a surface at a 40-degree angle, it bounces off at exactly 40 degrees, every single time. Law number 2, the incident ray coming in, the reflected ray bouncing off, and that imaginary perpendicular line we call the normal, they all lie perfectly flat in the exact same plane. These strict, unbending laws govern every single bounce of light in the entire universe. So, if the laws of reflection are totally unbending, how on earth do we manipulate them? Well, we do it by bending the surface itself. To Section 2, meet the spherical mirrors. These are basically our tools of the trade. Imagine taking a perfectly shiny hollow sphere and just slicing a piece right off. That curved piece, that's a spherical mirror. And there are two distinct types you need to know. Over on the left, we've got the concave mirror. This one curves inward, kind of like you're walking into a cave, which is a great way to remember it. We call this a converging mirror because that inward curve forces incoming parallel light rays to bounce and come together. On the right, we have the convex mirror. This one curves outward. It's a diverging mirror because its outward bulge takes those light rays and spreads them far apart. Now, for the rest of our time today, we're really going to focus on the incredible things we can do with that inward curving, converging concave mirror. Focus on the incredible things we can do with that inward curving, converging concave mirror. To really understand these optical illusions, we need a quick map of the terrain. P stands for the pole, basically the mirror's absolute center. The principal axis is the imaginary line running straight through it. C is the center of curvature. You can think of C as the exact center of that original imaginary sphere our mirror was sliced from. R is the radius of curvature, so the distance from the pole to that center. And finally, F is the focus. This one is absolutely crucial. The focus is the highly specific point where all those converging rays of light beautifully meet. Moving on to Section 3, the illusions of image formation. Let's see exactly how concave mirrors trick the eye. Now, I know this table might look a bit dense at first glance, but it actually tells a story of incredible dynamic change. It shows us how simply shifting your physical position completely changes the reflection you get. Look at case 1 at the top. If an object is far away, beyond C, the image is real, inverted, meaning upside down, and diminished or shrunk. But step a little closer, right at C in case 2, and the image stays upside down, but suddenly it's the exact same size as the object. Take another step in, case 3, between C and F, and boom, that upside down reflection is now heavily enlarged. Now skip all the way down to case 5 at the very bottom. If you step right up close between the pole and the focus, the physics flip completely. The image suddenly jumps behind the mirror, it becomes virtual, erect, meaning right side up, and significantly magnified. Just by taking a few steps forward, you've transformed a tiny upside-down reflection into a giant right side up one. But hey, you probably noticed I skipped a case on that table. Let's look at case 4, because this is where things get truly wild. When the object is placed exactly at the focus F, the image forms at infinity. Let that sink in for a second. By placing an object perfectly at that focal sweet spot, the mirror manipulates the light rays so they travel completely parallel to each other. They never cross. They literally cast an image infinitely far away. It is just a staggering reality of geometry and light. Move to Section 4, decoding ray diagrams. This is how we actually draw the magic. So we actually map out these visual illusions using what we call ray diagrams. Think of light rays as being bound by extremely strict traffic rules. There are three main pathways you need to know. First, if a ray travels parallel to the principal axis, it absolutely must pass through the focus after it reflects. Second, if a ray passes through the focus first, it has to bounce back perfectly parallel. And third, if a ray passes through the center of curvature, it simply reflects straight back along the exact same path it came from. The crucial point here is that these three pathways never, ever cheat. If you draw them out, they always follow the rules. Which brings us to the big reveal. When you take the time to actually draw those strict ray pathways from your object toward the mirror and back, the exact point on your paper where those reflected rays intersect is precisely where the visual illusion is going to appear in real life. It's like a giant puzzle. By just tracing a few simple lines on a piece of paper, you can perfectly locate exactly where an image will be. All right, Section 5, Real-World Mirror Magic, or the actual everyday applications of concave mirrors. Remember case 5 from our table earlier? The one where getting really close to the mirror creates a magnified right-side-up image? Well, we harness that specific trick all the time. It's exactly why we use concave mirrors for shaving and makeup. It lets us see our faces heavily enlarged and in super high detail. It's also the exact same tool your dentist uses to get a magnified view right behind your teeth. And remember case 4, where putting a bulb right at the focus sends light out to infinity? We use that for vehicle headlights, torches, and searchlights. By placing a light bulb right at the focus, F, the concave mirror blasts that light out into an incredibly powerful straight beam that just slices right through the dark. And that brings us right back to our opening hook, solar furnaces. This brilliantly illustrates the ultimate awe-inspiring power of a concave mirror. See, instead of putting a light bulb at the focus to send light outward, a solar furnace does the exact reverse. It takes massive amounts of incoming parallel sunlight, catches it on a giant concave mirror, and forces every single one of those rays to converge directly onto the single point of the focus. It concentrates so much light and therefore so much immense heat into one tiny spot that it literally creates a blazing furnace. We've covered a ton of fascinating ground today, so let's do a quick, energetic recap of this explainer. To sum it all up, reflection follows strict rules. Mirrors curve inward or outward to manipulate those rules. Your physical position entirely changes the image you see. Ray diagrams allow us to map it all out perfectly, and this geometry powers everything in our daily lives, from flashlights all the way to solar furnaces. It's pretty incredible to think about, really. Every time you flip down the makeup mirror in your car or turn on a flashlight in the dark, you're interacting directly with the precise mathematical laws of the universe. Which leaves me with one final provocative thought for you today. If a simple piece of curved glass can effortlessly bend light to create an image at infinity, or harness the sun's rays to melt solid steel, what other invisible laws of physics are quietly hiding in plain sight, shaping the visible world around you every single day? Thanks so much for joining me for this explainer. Keep wondering, and we'll see you next time.